Yet another variation on a mixing tank problem. So this one is a little bit different. We have 5 liters flowing in, 300, 5 liters flowing out. We have a concentration flowing in, fresh water to start with, but it says it's only valid for 0 to 10 minutes for T. So the reason it's only valid there is because at 10 minutes after you start the experiment, you all of a sudden change the concentration of water flowing in from 0.4 grams of salt per liter flowing in to 0 grams per liter flowing in. You have fresh water flowing in essentially. And so the question here is, what is the amount of salt in the tank at 15 minutes? All right, so that's the question we're going to be solving. So let's go ahead and dive in. So we're going to do q prime, so dq dt equals, and so let me just include my units. So that's grams per minute equals, okay, the salt going in. So that's 5 liters per minute times 0.4 grams per liter. So 5 liters per minute times 0.4 grams per liter. Let me make those dots a little bigger. Minus stuff flowing out. That's going to be the amount in the tank Q over 300. So that's 300. So that's grams per liter times the flow rate out, which is 5 liters per minute. All right, so we have our initial condition, Q at time 0 equals 0. We have a differential equation. If you do end up solving that differential equation, you end up with this. So there's not enough room, so I'm just gonna, I pre-solved it. All right, so you get Q of t equals 120 minus 120 e to the negative 1 over 60t. And so this is valid for the first 10 minutes, but we essentially need a new initial condition for over here when Q changes to a new function. And we're still going to keep the same timeline, so it's 10 minutes along. So in order to do that, we need what this function gives us at 10 minutes. And so we plug in 10 into that equation, and we'll get Q of 10 is approximately 18.42. So here we're going to use the value 18.42 as the condition at time t equals 10 for the grams of salt in the tank. What's kind of happening here, just to also show this as a graph, so if I have time and I have Q, the limiting concentration at the beginning is 120 grams, sorry, limiting amount is 120. We start at 0, we're going to go to 10 minutes, and right, so this is the part we would normally asymptote to, so it's going to do something like, let's see, you got up to 18, not very far, so something like that, and if it could, it would continue and asymptote up to there, but all of a sudden you change the ODE, and so what's going to happen is the new ODE is going to have a limiting concentration of 0, and if we go to 15, you're going to start going, let me change here, down, and you're going to start where you left off. And this one would continue forever and ever because it's as t increases there. So that's the idea here. So we solve the first differential equation. We're going to get a curve for that. It's limiting concentrations under 20. We plug in at 10 minutes. We got a value of 18.42. Sorry, the scale is a little off. All right, so left there. Then we're going to start a new differential equation, and our new initial condition is at time t equals 10 minutes. We're going to have 18.42 grams of salt in the tank. Right? So that's the idea here. So now we go and we have our new differential equation that we have to make. So that's dq dt. And right, that's grams per minute again. Equals, so this one's a little stranger, so we have 5 liters per minute flowing in, but we have 0 grams per liter concentration flowing in, salt flowing in. So that term really just disappears. There's no salt flowing into the tank. It's just fresh water. But we still have our minus, we'll still have our Q over 300 grams per liter times 5 liters per minute. There's still salt flowing out of the tank. All right, and since I don't nearly have enough room to solve all these equations, I pre-solved them. So if you actually solve that equation, so it's a little approximate because, right, this 18.42 is approximate, so The constant in front is approximate, but we get negative 1 over 60 times t. That's the 5 over 300 is where the 1 over 60 comes from. And then if we want to know, what is the amount of salt in the tank, 5 minutes after we start pouring fresh water in, well, that ends up being this number, right? So we plugged in 5 minutes later, so that would be at time 15 minutes. There's going to be approximately 16.95 grams of salt in the tank. All right, so once again, this is how you solve this variety of mixing tank problem. So usually you have some sort of tank setup happening for a limited amount of time, and then after that limited amount of time, it changes to a new setup, and you could have anything change. You could have the size of the tank change, you could have the flow rates change, you could have the salt concentration flowing in change. But the idea is you solve the first ODE for the first segment of time, you find the solution to that, then you're going to plug in the time that you transition from one to the next. So in this case, it was 10 minutes we transitioned. Then we figured out the number of grams in the tank at that time, and that's kind of our new initial condition for when we transitioned from one setup to the next. So we have 18.42. Then we solve another differential equation with just this one change parameter in this case. And we solve that, we get a differential equation, and then if we want to know the value, 5 minutes after the transition from pouring salt water in to pouring fresh water in, we have to plug in 10 plus 5, 15, and we'll get some number of grams of salt in the tank.